In this video, we are going to talk about Dalton's law, which relates partial pressures of gas mixtures. Dalton's law simply states that the total pressure of a gas mixture is equal to the sum of the partial pressures or the pressures of each component in that mixture. So another way of thinking about that is P total is equal to P1 plus P2 plus P3, etc., for however many gases you have. Each of the P1, P2, P3, for however many gases you have, that is the partial pressure of that gas within the mixture. This is very useful in detecting solid explosives because they can be detected by small amounts of gas phase. I don't know where that went. All right, gas phase molecules that are emitted by the explosive. Here are a lot of vapor pressures for some common explosives. So you can see they are very low, but if you have instruments that can detect them, then you can tell if there is an explosive in a container or not. You can also add substances in small amounts to explosives, and they can identify the explosives and track their origin. And you can do this by their partial pressures. The compounds that are added have high vapor pressures that are added to the plastic explosives, so it's easier to detect them by canines or electronic devices. If they have really high vapor pressures, it means that canines would be able to smell that gas. They'd be able to smell the gas that's emitted by the compound that has the high vapor pressure. So let's look at an example of Dalton's law. A gas mixture containing oxygen and nitrogen exerts a total pressure of 1.12 atmospheres. That tells me my P total is equal to 1.12 atmospheres. And that is equal to the pressure of oxygen plus the pressure of nitrogen. Now, if helium is added to the mixture, it increases the pressure to 1.75 atmospheres. So now my P total is equal to 1.75 atmospheres. And I can use this information to calculate the partial pressure of helium in the gas mixture. So if I know my P total is going to be equal to pressure of oxygen plus pressure of my nitrogen plus pressure of my helium. Well, I can plug in 1.12 for the pressure of oxygen and nitrogen together, and I can rearrange this to solve for the pressure of helium. So the pressure of helium is going to be equal to my P total minus the pressure of my oxygen plus the pressure of my nitrogen. My P total is 1.75, and the pressure of my nitrogen and oxygen is 1.12. So when we calculate this out, I can take 1.75 and subtract 1.12, which gives me 0.63 atmospheres. So this is the partial pressure of helium. In the next example, it has a mixture of three gases, has a total pressure of 3.54 atmospheres. So P total is equal to 3.54 atmospheres. The mixture is analyzed and found to contain 1.27 atmospheres carbon dioxide, so PCO2 is equal to 1.27 atmospheres, and 1.2 atmospheres of CO. So the partial pressure of my carbon monoxide is 1.2 atmospheres. If argon is the third gas present, what is the partial pressure? So that's what I'm going to be solving for. I know that P total for this problem is going to be the pressure of my CO2 plus the pressure of my CO plus the pressure of my argon. So though I can rearrange this to solve for the pressure of argon, and that's going to be equal to P total minus the partial pressure of carbon dioxide plus the partial pressure of carbon monoxide. Now I can plug my total pressure in, 3.54 minus the partial pressure of carbon dioxide is 1.27 atmospheres plus the partial pressure of carbon monoxide, which is 1.2 atmospheres. We can plug that into our calculators. And what do you all get? All right, I get 1.07. So the pressure of argon is going to be 1.07 atmospheres.